Pluto, a past planet that was scaled back to a dwarf planet, is still a topic of interest and study in the astronomical community. As later demonstrated by leading researchers, Pluto's and Neptune's orbits are dangerously close to ours. Astrophysicists Neil deGrasse Tyson and Michio Kaku are raising concerns about a potentially dangerous effect between these two planets, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike any other planet in the solar system. It needs a dazzling 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution. But Pluto's interest does not end there. Its orbit is marked by its exceptionally curved shape, deviating significantly from the near-circular orbits of the major planets. What makes Pluto's orbit even more curious is its tilt, set at 17 degrees to the ecliptic plane. Those who study its orbit find it significantly more extreme compared to other planets. This tendency and unpredictability add layers of complexity to its orbital design. One of the most interesting parts of Pluto's orbit is its intersection point with Neptune's orbit. For around 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, standing in contrast to what we might expect based on their general positions in the solar system. This prompts the natural question, why hasn't Pluto struck Neptune yet? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to determine its peculiar path in comparison to other planets, whose orbits lie mostly near the ecliptic plane. However, Pluto's orbit stands out due to its steep inclination and elongated shape. The mystery deepened with the realization that Pluto's orbit does indeed remain stable despite its proximity to Neptune. This stability amidst complexities is evidence of the intricate mechanics of space. The three-body problem, analyzing how three objects like Pluto, Neptune, and the Sun interact gravitationally, is key to understanding Pluto's path. Predicting these interactions is challenging, as each body pulls on the others in a constantly shifting gravitational dance. In Pluto's case, its orbit differs from Neptune's due to the Sun's gravitational influence, along with complex interactions involving key orbital mechanics concepts such as alpha libration, degree evaluation, and VZK oscillation. As demonstrated by astrophysicists, what keeps all planets in their orbits is a phenomenon known as alpha libration. In Pluto and Neptune's case, this means that whenever Pluto crosses Neptune's orbit, it is at least 90 degrees away from Neptune. This spatial separation is critical in preventing their orbits from crossing dangerously. On the other hand, the vertical movement of a body in its orbit, called expansion libration, adds another layer of protection. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned well above their orbital plane. Another significant consideration is VZK oscillation, named after three researchers, von Zeipel, Kozai, and Leadoff, who studied how objects move in space. It describes how three celestial bodies, like Pluto, the Sun, and Neptune, exert gravitational influence on one another. In Pluto's case, this oscillation explains why its orbit remains stable despite its unusual path. Although Pluto's orbit may seem erratic, the VZK oscillation helps keep it on a predictable course for billions of years. This phenomenon highlights how seemingly chaotic movements in space are actually governed by patterns and forces. Together, these factors help maintain Pluto's orbit, ensuring it doesn't crash into Neptune or become lost in the vastness of space. Understanding this trio of celestial bodies, Pluto, Neptune, and the Sun, is crucial for comprehending how gravitational forces shape planetary motion. Studying these interactions enhances our knowledge of Pluto, the solar system, and even distant exoplanets. Mathematical simulations in the late 1980s demonstrated that despite Pluto's stabilizing orbital features, small variations in initial conditions could lead to significant changes over time. However, these seemingly chaotic properties have been found to maintain long-term stability, keeping Pluto's orbit in check. Recent computer models have provided deeper insights into how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path. A special resonance exists between Neptune and Pluto. Whenever Pluto completes 2 orbits around the Sun, Neptune completes 3. This synchronization helps maintain Pluto's orbital stability. But Neptune isn't the only planet influencing Pluto. Jupiter's gravity also plays a crucial role. Studies show that Jupiter's immense gravitational pull helps stabilize Pluto's orbit over extended timescales, possibly even billions of years. Along with Neptune and Saturn, Jupiter acts as a safeguard, preventing Pluto from veering off course. These orbital peculiarities are crucial in maintaining the broader stability of the solar system. Without such mechanisms, the solar system could be far more chaotic, with bodies like Pluto potentially colliding with others or being ejected from their stable orbits. Such disturbances could have cascading effects on other planets and celestial objects. For Pluto, particularly in discussions about its potential interactions with Neptune, understanding its orbit is essential. This knowledge provides a clearer picture of the dynamic nature of the solar system. Pluto's case demonstrates that even seemingly unstable orbits can reach a state of equilibrium through the intricate interplay of gravitational forces and orbital mechanics. Continued observation and study of these peculiarities remain vital to improving our understanding of the universe. Exploring the depths of space often reveals unexpected complexities, and Pluto's orbit is a prime example of this phenomenon. The concept of orbital chaos, the delicate dependence of a body's path on its initial conditions, is clearly illustrated in Pluto's case. Even slight changes in Pluto's speed or position can dramatically alter its long-term trajectory. Within our vast solar system, Pluto occupies a unique position that challenges our understanding of planetary dynamics and classification. Since its discovery in 1930, Pluto has been extensively studied, leading to significant revelations about its behavior and composition. One of the most intriguing aspects of Pluto is its surface, a complex landscape of ice, rock, and various compounds. The New Horizons mission, which flew by Pluto in July 2015, provided incredible data about this distant world. Pluto's surface features enormous icy plains, towering mountains, and deep valleys, further proof that this dwarf planet remains one of the most fascinating objects in our solar system. Pluto's mysterious surface and atmosphere. The data from the New Horizons mission revealed that Pluto's surface is far more dynamic than previously imagined. One of its most striking features is Sputnik Planitia, a vast, nitrogen ice-filled basin that dominates Pluto's heart-shaped appearance. This region, part of the larger Tombor Regio, is thought to be geologically active, with convective ice flows reshaping its surface over time. Additionally, Pluto boasts mountain ranges composed of water ice, some reaching heights of nearly 6,500 meters, 21,300 feet, comparable to the Rocky Mountains on Earth. These icy peaks contrast sharply with surrounding plains, further indicating a complex and evolving landscape. Scientists believe Pluto may even harbor cryovolcanism, where subsurface reservoirs of liquid water or slushy ice erupt onto the surface, reshaping its terrain. Beyond its surface, Pluto also has a tenuous but fascinating atmosphere. Composed primarily of nitrogen, N, methane, CH, and carbon monoxide, CO, this thin atmosphere extends hundreds of kilometers above the surface. However, due to Pluto's weak gravity, much of its atmospheric gases gradually escape into space. The seasonal changes of Pluto. Unlike Earth, which experiences 4 relatively short seasons due to its 23.5 degrees axial tilt, Pluto's extreme 122 degrees axial tilt causes highly exaggerated seasonal variations. Given its 248-year orbital period, each season lasts for decades rather than months. When Pluto is closer to the Sun, perihelion, its atmosphere expands due to the increased warmth, allowing gases to rise and form hazy layers. Conversely, as Pluto drifts farther from the Sun, aphelion, its atmosphere condenses, with nitrogen frost and methane snow settling back onto the surface. These seasonal shifts significantly alter Pluto's landscape, affecting everything from the color of its surface to the distribution of its ice deposits. Some scientists believe that over time, this cycle could lead to long-term changes in Pluto's appearance and even its atmospheric composition. Pluto's place in the Kuiper Belt. Pluto is not alone in the outer reaches of the solar system. It resides in the Kuiper Belt, a vast region beyond Neptune that contains millions of icy bodies, remnants from the early formation of the solar system. Alongside Pluto, other large Kuiper Belt objects, KBOs, such as Eris, Haumea, and Makemake share similar characteristics. These bodies provide valuable clues about planetary evolution and the early history of our solar system. One of the most intriguing aspects of Pluto's location is its relationship with other trans-Neptunian objects, TNOs. Many of these objects, including Pluto, are in resonant orbits with Neptune, meaning their gravitational interactions prevent collisions while maintaining long-term orbital stability. This resonance has preserved Pluto's unique orbit for billions of years. Could Pluto be reclassified as a planet? Ever since Pluto was reclassified as a dwarf planet by the International Astronomical Union, IAU, in 2006, debates have continued over its planetary status. The primary reason for Pluto's demotion was its inability to clear its orbit, a criterion established by the IAU's planetary definition. Because Pluto shares its orbital zone with other Kuiper belt objects, it does not meet this requirement. However, many scientists argue that Pluto should still be considered a planet due to its complex geology, atmosphere, and moons. Some researchers propose revising the planetary definition to focus on intrinsic properties rather than orbital characteristics. If such changes were adopted, Pluto, and potentially hundreds of other celestial bodies, could regain planetary status. Pluto's moons and their impact. Pluto is not a lonely wanderer. It has a system of 5 known moons, the largest and most significant being Charon. With a diameter of 1,212 kilometers, 753 miles, more than half the size of Pluto itself, Charon is so massive relative to Pluto that the two bodies orbit a common center of mass, effectively making them a binary system. The other moons, Styx, Nix, Kerberos, and Hydra, are much smaller but still play a role in shaping the system's dynamics. These moons likely formed from a giant impact event, similar to how Earth's moon was created. Their irregular orbits and chaotic rotations add further mystery to Pluto's already complex gravitational environment. The future of Pluto exploration. The New Horizons flyby in 2015 provided unprecedented data, but many questions remain about Pluto and the outer solar system. Future missions could focus on sending an orbiter to study Pluto for an extended period, capturing long-term changes in its atmosphere, surface activity, and interactions with the Kuiper belt. Some scientists even speculate about landing a probe on Pluto, which could provide direct surface analysis and possibly reveal hidden subsurface oceans. Pluto remains one of the most enigmatic and scientifically rich worlds in our solar system. Whether classified as a planet or a dwarf planet, its complex orbit, dynamic surface, and unique atmosphere make it a celestial body worth studying for generations to come. The most striking aspect of Sputnik Planum is a massive heart-shaped plain primarily composed of nitrogen ice. In this area, a wide variety of geological features are exhibited, including large ice blocks and what appear to be moving glacier. The presence of these characteristics suggests that Pluto may still be geologically active despite its considerable distance from the Sun. Additionally fascinating is the low-temperature aspect of Pluto's atmosphere, which consists primarily of nitrogen with traces of carbon monoxide and methane. Pluto has a thin atmosphere, but it exhibits intriguing seasonal variations. As Pluto orbits the Sun, its atmosphere can expand and become more dynamic. This behavior demonstrates the intricate interaction between Pluto and its atmosphere. During its closest approach to the Sun, gases in the atmosphere may freeze onto the surface. As it moves farther away, these gases can re-evaporate back into the atmosphere. The relationship between Charon, Pluto's largest moon, and Pluto itself also complicates the system. Charon is considerably large, with a diameter about half that of Pluto. This size ratio means that the barycenter, the point in space around which both bodies orbit, lies between them rather than within Pluto itself. This unique relationship plays a role in the area's gravitational dynamics, influencing the orbits of other objects in the Kuiper belt. The Kuiper belt, located beyond Neptune, is home to a small population of icy bodies, including numerous additional dwarf planets. This region serves as a reservoir of ancient material from the early solar system, offering researchers valuable insights into its evolution. Pluto's orbital characteristics may provide clues about the movement patterns of these distant objects, suggesting that interactions with more massive planets could have significantly shaped their current orbits. One key implication of studying Pluto's orbit is its potential impact on our understanding of the solar system's evolution. Gravitational influences from giant planets, similar to how Jupiter and Neptune alter the trajectories of smaller bodies, can lead to changes in orbits, potentially causing collisions or ejections from the solar system. As researchers continue to study these interactions, they may reveal broader patterns of behavior followed by celestial bodies across the universe. The study of Pluto also raises philosophical questions about classification in cosmology. The decision to reclassify Pluto as a dwarf planet in 2006 sparked discussions about what defines a planet. The International Astronomical Union's definition focused on criteria such as orbital dominance and size, leading many to debate the implications of such classifications. This ongoing debate reflects our evolving understanding of the universe and underscores the need for a flexible approach to categorizing celestial bodies. Furthermore, the potential for future exploration of Pluto and the Kuiper belt remains an exciting frontier. With advances in technology and mission planning, scientists are considering sending additional spacecraft to study Pluto and other objects with similar orbital characteristics. Such missions could provide valuable information about the primordial substances that shape the solar system, possibly offering insights into the origins of life on Earth. The study of exoplanets, planets beyond our solar system, is another intriguing field that intersects with our understanding of Pluto. As astronomers discover an increasing number of exoplanets, particularly those in the habitable zones of their stars, lessons learned from studying our own solar system may help develop theories about planetary formation and habitability. Public interest in Pluto has remained strong, thanks in part to its mysterious status and the stunning images returned by the New Horizons mission. The dwarf planet has captured the imagination of people worldwide, inspiring a renewed appreciation for the vastness of space and our place within it. As we continue to uncover the mysteries of Pluto and the celestial bodies in its region of the universe, we are reminded of the awe-inspiring wonders the cosmos has to offer. Pluto's extraordinary nature extends beyond its physical attributes and orbit. It also serves as a significant case study for understanding planetary development and the dynamics of celestial bodies. Pluto's evolution is believed to have occurred alongside other Kuiper belt objects in the early solar system. Studying its composition can provide insights into the conditions that prevailed during the formative stages of the solar system, shedding light on how Earth-like planets will be studied in the future. Some evidence even suggests that Pluto might possess a subsurface ocean, a discovery that could alter our understanding of its geology and the potential for life. Data from New Horizons indicate that some regions of Pluto's surface, such as its icy mountains, may be composed of water ice, which behaves differently than typical rock at extremely low temperatures. This discovery raises the possibility of liquid water existing beneath Pluto's frozen crust, prompting intriguing questions about the potential for life in such extreme conditions. Additionally, Pluto's relationship with its atmosphere has the potential to shed light on atmospheric science. The seasonal changes in its thin atmosphere provide a natural laboratory for studying planetary atmospheric cycles. Researchers are particularly interested in how interactions between solar radiation and Pluto's surface can lead to complex weather patterns, much like those observed on larger planets. The study of Pluto continues to shape our understanding of planetary science in profound ways. Its complex geology, atmosphere, and interactions with its moon, Charon, provide valuable insights into the dynamic processes that govern celestial bodies in the outer solar system. The presence of possible cryovolcanism, volcanic activity involving the eruption of water, ammonia, or methane instead of molten rock, raises questions about internal heat sources that may still be active beneath Pluto's icy surface. One of the most surprising discoveries made by the New Horizons mission was the youthful nature of some of Pluto's surface regions. Unlike many other celestial bodies in the Kuiper belt, which bear the scars of countless impact craters, large portions of Pluto's surface appear relatively smooth. This suggests that resurfacing processes, such as glacial activity or cryovolcanism, have reshaped these areas in the recent geological past. Such activity challenges previous assumptions that small, distant worlds like Pluto are geologically dead. Pluto's role in comparative planetology. Studying Pluto provides a valuable comparison to other icy worlds in the solar system, such as Neptune's moon Triton and Saturn's moon Enceladus. Triton, believed to be a captured Kuiper belt object, shares many similarities with Pluto, including its retrograde orbit and nitrogen-rich surface. Understanding Pluto's composition and history helps scientists draw parallels between these distant worlds and refine theories about planetary migration and evolution. Additionally, Pluto's extreme seasonal changes offer a unique perspective on how atmospheres behave under varying solar influences. Unlike Earth, where seasons are driven primarily by axial tilt, Pluto's seasons are influenced by both its tilt and its highly elliptical orbit. This results in long, dramatic shifts in temperature and atmospheric density over its 248-year journey around the Sun. Observing these changes helps researchers model similar processes on exoplanets, where extreme orbits and variable atmospheres may also play a role in habitability. Future exploration of Pluto and the Kuiper belt. Although New Horizons provided a wealth of information about Pluto, many questions remain unanswered. Scientists are advocating for future missions, possibly including an orbiter that could study Pluto over an extended period. Such a mission would allow for detailed observations of its climate cycles, internal structure, and the potential existence of a subsurface ocean. Beyond Pluto, the Kuiper belt remains a largely unexplored frontier. The belt contains countless icy bodies, some of which may harbor clues about the formation of the solar system. Objects like Arakoth, which New Horizons visited after Pluto, reveal primitive material that has remained largely unchanged since the solar system's birth. Continued exploration of these bodies could provide crucial insights into the building blocks of planets and the processes that shaped our cosmic neighborhood. Pluto's place in the ongoing planetary debate. Pluto's reclassification as a dwarf planet in 2006 by the International Astronomical Union, IAU, remains a topic of debate among astronomers and the public. The decision was based on three criteria for planet classification. 1. The object must orbit the Sun. 2. It must be massive enough for its gravity to shape it into a nearly round form. 3. It must have cleared its orbit of other debris. While Pluto meets the first two criteria, its orbit overlaps with other Kuiper belt objects, failing the third criterion. However, some scientists argue that this definition is too restrictive and does not account for the diversity of planetary bodies in our solar system. The debate over Pluto's status underscores a broader conversation about how we define celestial objects and whether the classification system should evolve as we learn more about distant worlds. The broader significance of Pluto. Pluto's study extends beyond planetary classification. It provides a window into the outer solar system's history and its connections to exoplanetary systems. As astronomers discover more exoplanets with unusual orbits, extreme climates, and icy surfaces, Pluto serves as a valuable reference point for understanding these distant worlds. Moreover, Pluto continues to captivate the public imagination. The breathtaking images and scientific revelations from New Horizons have inspired a new generation of space enthusiasts. Pluto's story, once a planet, then reclassified, and now recognized as one of the most intriguing objects in the solar system, illustrates the evolving nature of scientific discovery. Conclusion. As we continue to explore Pluto and the outer reaches of our solar system, we are reminded that the universe is full of surprises. Pluto's unique characteristics, from its icy plains and towering mountains to its dynamic atmosphere and complex orbital interactions, challenge our understanding of planetary science. Future missions to Pluto and the Kuiper belt will likely uncover even more secrets, expanding our knowledge of the solar system's formation and evolution. In the grand scheme of space exploration, Pluto remains a symbol of curiosity and the relentless pursuit of knowledge. Whether classified as a planet or a dwarf planet, it stands as a testament to the wonders of the cosmos, reminding us that even the most distant and seemingly small worlds can hold profound scientific significance.